Hi, welcome to Lecture 3 for our Introductory Statistics course in Psychology, Psych 2317. Now, in Lecture 2, which is linked below, we introduced the notion of standardized scores. We called them Z-scores, and these allow us to compare scores on one measurement scale to scores on another scale. And you might remember that there's a nice formula for doing this. We have this formula Z equals x minus mu over sigma. And what that really means is simply take the raw score, subtract the mean, and then divide by the standard deviation. And remember that this tells us the number of standard deviations that a raw score is away from the mean. If it's positive, that means that the raw score is above the mean. And if it's negative, that means that the raw score is below the mean. And we did an example last time. We'll just recap this real quickly. Suppose we had two applicants that took some college entrance exams. So you had applicant 1 who scored a 1270 on the SAT, and because the mean of the SAT was a 1060, we know this is 210 points above the mean, which we reasoned last time is one standard deviation above the mean. Whereas applicant 2, they scored a 30 on the ACT. So we want to know who did better, right? Who did better on their respective test? Now the ACT, we know, has a mean of 21 with a standard deviation of 9. And if we have this person with a 30, that means they scored 9 points above the mean, which turns out to be 1.5 standard deviations above the mean. And we can see these calculations here in terms of Z-scores. For applicant 1, the Z-score would be found by taking their raw score minus the mean of the SAT, which was 1060, and then dividing that difference by the standard deviation, 220. And since the difference and the standard deviation are equal in this case, that gives us a Z-score exactly 1. This means that applicant 1 scored 1 standard deviation above the mean. On the other hand, look at applicant 2. They scored a raw score of 30. So 30 minus 21, which is the mean for the ACT, divided by the standard deviation of 6, that gives us a difference of 9 divided by 6. 9 divided by 6 is 1.5. So applicant 2 scored 1.5 standard deviations above the mean. And so we reasoned again last time that applicant 2 must have the higher standardized score. This is not possible unless we were to compute Z-scores, to standardize these two different scales to be comparable on the same scale. So that established the importance of Z-scores. Now we're going to do something similar this time, but we're going to ask a slightly different question. The question this time is, what if instead we wanted to compare a single measurement to the distribution of all other possible measurements? Let me give you an example. Suppose again that we scored a 30 on the ACT. So you got this score. We can ask two equivalent questions. The first question that we might be interested in asking is, what proportion of all other test takers scored below your score of 30? This sometimes is called what is the percentile rank. So I'll just write that out to the side. I probably won't use that notion very often in this course, but that is equivalent to this question. What proportion or percentage of all other test takers scored below your score of 30? An equivalent question could be, what is the probability that a randomly chosen test taker scores below your score of 30? Now, both of these questions might sound a little different, but they both have the same answer. They are asking the same information about your score, 30, compared to the distribution of ACT scores. And so all through this semester, we will use these two notions perhaps interchangeably because they are very much related to each other. So how on earth would we answer a question like this? Well, to answer this, we need to know something about how all of the other test taker scores are distributed. And that's what's going to start our new thing for today. Today, we're going to note that for most tests, the distribution of scores form what is called a normal distribution. You may have heard this term before. In fact, you may have seen this curve. You may have seen something that looks like a bell-shaped curve. That is a typical figure or a typical graph of the normal distribution. So for example, this might be my distribution of ACT scores, and you'll notice some things. It's on the scale of ACT scores, and particularly here is my score right here. It's halfway in between 27 and 33. So a couple of questions before we get into the question that we're interested in, which were these two equivalent questions. Let's talk a little bit about this drawing. How did I know to draw it like this? Well, that's because I know a few facts about the normal distribution. Let's look at those facts. First of all, the normal distribution is peaked at the mean. So since ACT scores have a mean of 21, that tells me that this curve is going to have its peak right here at 21. So this is the mean of this distribution. It's right in the middle. The other thing that I might note is that normal distributions are symmetric around the mean. That means that whatever shape it has on this side, so this slowly descending part here, is going to be reflected on this side. They are essentially mirror images of each other. Okay. Another thing is that the width of this distribution, or the width of this curve, is controlled by the standard deviation. In fact, I can tell you that it is controlled this way. This distance right here, okay, from the center axis of symmetry to this little point, which I'll make a note right there, that's called an inflection point. I'll mention what that is in just a second. The important thing, though, is that that distance is equal to the standard deviation. That distance is equal to, as for ACT scores, that is 6 points. All right. So how do I know how wide that's supposed to be? Well, you'll notice when I look at this curve, this part right here is kind of curved downward. All right, that's called negative concavity. Whereas this part is, the curvature kind of points upward, right? It kind of looks like that. So the point at which the curvature changes from being downward pointing to upward pointing is called the inflection point. And so this distance right here is going to be absolutely equal to the standard deviation. And so I just say that in general by saying the width is controlled by the standard deviation. So you'll notice, having those three pieces of information, I can make this sketch right here that's centered at the mean and that pokes out about 6 units this way and 6 units this way before it starts tailing off. And that gives me a picture of this distribution of ACT scores, this normal distribution. In fact, we say that the normal distribution is completely described by 2 parameters. These parameters, let me highlight that, that's an important new word for us. These parameters, of course, are what we're used to, mu and sigma, the mean and the standard deviation. Okay? So normal distributions are used in a lot of different contexts, but for us, in a psychology context, we very, very often see them in the context of test scores. So that's what we're going to use for our example today. So how do we answer our question? Well, at the risk of making you dizzy, let me roll back to those questions. The questions were, what proportion of all other test takers score below 30? Or another way to ask that is, what's the probability that a randomly chosen test taker scores below 30? So how do we answer that question? Well, I want to outline 4 different ways to answer that question. Now, only one of which I will actually show you how to do today. The first one is we could use calculus. Okay, so if you've ever taken a calculus course, this will be absolutely obvious to you. If you've never taken a calculus course, this will be absolutely not obvious to you. But in a nutshell, what happens is, to answer this question, we are looking for the area under the curve. We're looking particularly, in fact, I'll draw it here for us, we're looking for this proportion right here. Okay, so we're looking for what proportion of that curve is less than my score of 30. All right, see, that's a pretty big proportion. Exactly what it is, I don't know. But I could use calculus to find that out, because calculus, in fact, integral calculus, or using integration, is exactly the right thing to use for such a problem. But we don't have to do this, okay? If you take a mathematical statistics course, then you'll learn how to do that. But that requires you, of course, to take calculus. So what if you can't use calculus? What do? Well, the classical approach was to use statistical tables. Now, I wish I had one of the big CRC statistical table books here, but I don't. But if you have any normal old statistics book, you'll probably notice that at the end of the book, it has some appendices, and these appendices are just a bunch of tables of numbers. And those were a very typical way of doing these kinds of problems. I will say that this is mostly an antiquated method now. There are perhaps better ways to do it. In fact, one that I will show you today. But at the risk of saying that I'm antiquated, I guess I'll say that statistical tables are antiquated. So what if you can't use those? Well, then the next thing you might consider is to use some statistical software. Okay, now we're getting somewhere. So these are things like R or JASP, which I'll introduce you to a little bit later this semester, and there's others as well. R and JASP I mentioned because they're free and very powerful. But I say there's a problem. These are great packages. I absolutely use these in most of my courses past this course, but they do too much for us right now. All we want to do right now is answer the question about what proportion of exam scores are less than 30, or what's the probability that a randomly chosen test taker will score less than 30. We don't need R and JASP to do this for us. In fact, it's actually kind of hard to make, particularly JASP, do this. R, it's actually quite easy with a little bit of know-how, but nonetheless, they're too much. The tools are too effective for what they do for us right now. So I've got a little bit of a simpler thing that we can do. So instead, what we are going to use a lot this semester is we're going to use a custom thing that I developed for this course. We're going to use an interactive web application. It's just something that I wrote in a programming language called Shiny, and it's used to calculate things from distributions. The advantage of this program, and I'll demonstrate it for you in a second, is there's no installation of anything necessary. You don't have to install JASP or R. If you've got a phone, you can use it. In fact, I'll show you what it looks like on a phone in just a second. Now, if you're watching this from a computer, all you have to do is go to a browser and type in this web address. Okay, now it's kind of a long address, but it's basically my name, Tom Faulkenberry, .shinyapps.io/dist_calc. It's a distribution calculator. Again, it's kind of a cumbersome name, so if you would rather, you can just aim your phone camera at this little QR code right here, and it'll pop it right up on a phone for you. So what I want to do now is I want to show you this website, and also want to show you what it looks like on a phone real quickly. So let's look at the website first. So I'm going to pop over to a browser real quickly, and this is what happens when you type in that web address. In fact, let me reload it real quick just to make sure we're working from a fresh copy. Okay. So again, this completely works within your browser. You can use Chrome, Safari. I think it works for Internet Explorer, though I haven't tested it. Should work for most everything. So the idea is you can specify your distribution, and you can give some things you know about the problem. So you can give things like the mean and standard deviation. And then from that, you can find areas under the curve. In fact, you can find 4 different types of areas. You can find a lower tail, an upper tail, both tails, or the middle. Okay. What are those? Well, think about them for a minute. The lower tail, let me just click that, is going to be a lower tail past some point, whereas an upper tail will be the upper part past that point. If you did both tails, that would give you this tail and this tail for 2 given numbers. And then if I wanted the middle, it would give me the opposite. Okay. So for a given problem, we have to kind of think, what is the picture that I'm trying to solve here? So we'll talk about that. Well, let's look at our problem. Okay, let's look at the problem that we set out to solve, which was what proportion of ACT scores are less than 30. So what I need to do is, first of all, I need to make sure that I'm using a normal distribution. You'll notice if you click this drop down, it gives me some other stuff that if this is your first course, you won't know what T or F mean, and don't worry about those for now. We'll deal with those later. Normal is the default, so that should be what has popped up here. You can see your little normal distribution over on the right. We want to go ahead and set the mean and standard deviation. So for an ACT distribution, as we've discussed several times, the mean is 21 and the standard deviation is 6. So if I just type those in, then I get a distribution that is now centered at 21 and goes out according to the scale that we drew by hand a second ago. Now what we are wanting to find is the proportion of scores less than 30. So what we're trying to find is a lower tail, but we're trying to find the lower tail of things from 30 to the left. So I need to change this value of A right here, which defaults to some weirdly chosen number. I'm going to change that value of A to 30. And then when I do that, it automatically updates in the window and gives me exactly the picture that I'm looking for. The proportion of scores that are less than 30 in this distribution, and you can see that's the shaded part, is this proportion right here. It's 0.933 or 93%. Also, notice the notation here. This notation, P of x less than 30, that's a probability notation. That says that the probability that x is less than 30 is 0.93. So the two questions that we asked, namely, let me scroll back up here and then I'll pop it back over to the window here in a second. The question that we asked were what proportion of all other test takers score below 30, and what is the probability that a randomly chosen test taker scores below 30? Well, the answer is, according to our app, the answer is 0.93. Okay, so it's a pretty high proportion. Of course, the biggest proportion we could get would be 1. That would mean 100% or all of the curve. But this is the answer to our question. So real quickly, let me summarize. I did write on the notes here. Let me do it this way. I did write on the notes on my tablet exactly those steps so that if you're watching along with this later, you can see what those steps are. Again, you have to set the distribution, set your mean and standard deviation. You have to set the find area part for this problem to lower tail. Other types of problems that we can practice with later, those will have to be set accordingly, and then we set the number A to something that makes sense. And so that tells us again the proportion of scores less than 30 is 0.93. You might be interested to know how does this work on the phone? For example, if I were to click that QR code that was just right up here, what would it look like on my phone? Well, I actually happen to have it here. I'm going to reload it and then I'm going to drop my phone in and share that screen. Okay. And it'll take just a second. And there it is. This is what it actually looks like on an iPhone 5. Yeah, here we go. So it's the same screen, it's just a little squashed. So instead of having a left to right orientation, you have all your stuff here. You have to go down for the picture. So let's just recreate this problem. The mean is 21, so I just type that in there. Standard deviation is 6, okay? And then I want the lower tail, and then I want the lower tail from 30 to the left. And then if I go just say done to clear up my screen, I go look at my curve and notice I get exactly the same, 0.93. So the user interface I need to tweak just a little bit for phones, but I think if you do it sideways, you might get a little bit better. You can shrink it, you can blow it up, you can do all kinds of things with it. So anyway, it works kind of nicely on your phone. So if you're sitting in class and you don't have a laptop with you, then you can still use this calculator to your advantage. So let me pop back over to the iPad now. I'm done with the phone. Okay, so that's how we do that calculation in the web app. I do want to show you one more way to do this exact same thing, and that is to use the standard normal distribution. So what is that? Well, a standard normal distribution is actually the one that the web app gives you by default. In other words, it's a normal distribution where mu and sigma, the mean and standard deviation, are set to 0 and 1, respectively. So let me go back to the web app. I'm just going to reload it so that I get the defaults. And you'll notice that by default, the mean is 0 and the standard deviation is 1. So the default on this calculator is the standard normal distribution. So how do we do this? Well, basically there's one extra step that we have to do. And that extra step is what we did last time. We have to convert the raw score to a z-score. And of course, we've already talked about how to do this. This is a z-score of 1.5. Then what we do is we go back into our web app and we just use the defaults, but then we specify a equals 1.5. The threshold that we're considering this time is that z-score. So let's pop over to the web app and see how that's done. Again, we want the lower tail because we're wanting stuff to the left. If we were asking how much is greater, we would use the upper tail. I'm going to set a to 1.5 this time. Notice it gives me the same picture, okay, as the last time, but this time the numbers down here, these are no longer ACT scores, but instead they are standardized z-scores. But notice the probability is exactly the same. This is actually typically the way you're going to want to do this. The reason is not quite clear yet, but if you're just popping into this little web app, this means all you have to change is this stuff down here. You can leave the mean standard deviation to be standardized. So it's kind of a nice thing. So let's wrap up real quick. Why would you even consider doing this? Well, I'll just mention for now that later we're going to be using other standardized distributions. So did you see that T and that F up there? That's a hint. We're going to be getting there. We're going to use some other standardized distributions that will require this step. We will have to compute something like a z-score for those. And so it's good to get into the practice right now. And I will say this is the method that was used for the, if I mentioned up here above, the statistical tables method. So this one right here, this was exactly what you used to have to do because the statistical tables just gave you the standard normal distribution. They didn't give you any of the other special ones. So anyway, this is what we do. So I do hope that you enjoyed this. I hope you will find this web app interesting. If you're not in my class and just watching this, do try to figure out ways that you can use this web app in your own work or in your own teaching. But that's all for now, and we will see you at the next lecture. The next time, what are we going to do? We're going to talk about what happens when we sample things, right? Because our goal is to make model comparisons based on collected data. Collecting data means we're pulling samples, and so we need to know something about how samples are distributed, how samples stack up. It's going to be really exciting. So we'll talk about that next time. That's all for now. See you then.